Good afternoon, everybody. Hope you had a good weekend and you're ready to learn about black holes today. So I have a couple of announcements. The first one is for everybody. Just remember that you have a midterm next Monday during class time. Same format, same everything as last time. The only thing that is different is the material that it covers. It covers homework 4 through 6 and lectures 10 through 17. So that's for everybody. And then the next announcement is only for people who have discussion sections on Thursdays. So for you, if that is your case, you may know that we have a holiday this Thursday. It's a Veterans Day. So the campus will be closed and you will not have discussion sections in person. I spoke to the TAs and their plan is to give you 2 quizzes campus. The bad news is you'll have 2 quizzes next time. Oh, I froze. I see that. All right, let me wait for a second, see if okay, hold on. Everyone seem to be freezing. All right. So I don't know if you guys can hear me, but please. Oh, I'm back. I think I'm still frozen. You can still hear the video is frozen. Okay, the video different network. All right. All right, can you guys hear me all right? Okay, great. Okay, so I'm using my iPhone. I'm using my hotspot. I'm not sure if I start freezing again and if somehow we lose the connection completely. Make sure you check YouTube later on. I will finish the lecture and I will post it. But sorry about that. I hope it works. All right, so let me repeat the announcement for people on discussion sections on Thursday. So again, there will be no discussion sections this Thursday. It is a holiday. Campus will be closed. So instead, people who normally go to discussion section on Thursday, you get to stay home. You don't have to go, but you will have 2 quizzes next week. I realize you're at a somewhat of a disadvantage because you will not have the full hour to go over the homework. So if that is the case, I do encourage you to attend one of our virtual office hours. Technically, I will not have my office hours on Thursday because it is a holiday. However, I'm happy to do it. So if you want to meet with me on Thursday, if you would like me to have a session where I go over homework number 6 with you, just send so that I know that there are actually people who are interested. Happy to have discussion, not discussion section, sorry, just my office hours, my virtual office hours on Thursday at 2 p.m. So just let me know if you plan to come. All right. There's each of the TAs also have a virtual office hour. They are all listed on iLearn under faculty info. I think it's what it's called. So just go check it out and make sure that you get the help that you need. Am I still freezing, you guys? Is that the case? So a little bit every now and then. Okay. I think as long as you can hear me well, I mean, I can also turn off my video. Right, I can turn off my video. You get my picture. You don't get to see my hands. All right. Okay, let me try this for a little while. And let me go on to our class. And again, if I'm freezing or whatever, just let me know. I can just record the lecture and post it later. But since you're here, we might as well do this. All right, so last time we talked about white dwarfs, which were the type of core that was left behind after a low mass star had a planetary nebula when all the gases go away, and then what is left behind is the core. And the core of a white dwarf, we talked about how it was supported by degeneracy pressure from electrons. All that meant was when electrons are compressed and they're forced to occupy the same place at the same time with the same energy or momentum rather, they start moving faster because they cannot occupy the same place at the same time. So the fact that they're moving faster, that exerts a pressure, and this pressure is called degeneracy pressure. So that's what balances gravity in a white dwarf, but there's only so much gravity that they can balance. And so that's when a white dwarf is more than 1.4 solar masses, then it cannot be a white dwarf anymore. The electron degeneracy pressure fails, and so everything collapses, and then we get the next type of object, which is a neutron star. And we're going to talk about that today briefly, and then we will move on to black holes. And then we'll talk about black holes for the rest of the week. So a neutron star is what's left. It's one of the two possibilities of core that is left behind after a supernova in a high mass star. So the mass of a neutron star is somewhere between 1.4 solar masses and about 3 solar masses. So let's talk a little bit about neutron stars. And I have a video. I don't know if it'll play okay. So I'll play it for you guys. You let me know if you were able to hear it okay. And if not, we'll have to skip videos today. But here we go.
Stars exist because of a fragile balance. The mass of millions of billions of trillions of tons of hot plasma are being pulled inwards by gravity and squeeze material together with so much force that nuclei fuse. Hydrogen fuses into helium. This releases energy which pushes against gravity and tries to escape. As long as this balance exists, stars are pretty stable. Eventually, the hydrogen will be exhausted. Medium stars like our Sun go through a giant phase where they burn helium into carbon and oxygen before they eventually turn into white dwarfs. But in stars many times the mass of our Sun, things get interesting when the helium is exhausted. For a moment, the balance of pressure and radiation tips and gravity wins, squeezing the star tighter than before. The core burns hotter and faster, while the outer layers of the star swell by hundreds of times, fusing heavier and heavier elements. Carbon burns to neon in centuries, neon to oxygen in a year, oxygen to silicon in months, and silicon to iron in a day. And then, death. Iron is nuclear ash. It has no energy to give and cannot be fused. The fusion suddenly stops and the balance ends. Without the outward pressure from fusion, the core is crushed by the enormous weight of the star above it. What happens now is awesome and scary. Particles like electrons and protons really don't want to be near each other. But the pressure of the collapsing star is so great that electrons and protons fuse into neutrons, which then get squeezed together as tightly as in atomic nuclei. An iron ball the size of the Earth is squeezed into a ball of pure nuclear matter the size of a city. But not just the core, the whole star implodes, gravity pulling the outer layers in at 25% the speed of light. This implosion bounces off the iron core, producing a shock wave that explodes outwards and catapults the rest of the star into space. This is what we call a supernova explosion, and it will outshine entire galaxies. What remains of the star is now a neutron star. Its mass is around 1 million times the mass of the Earth, but compressed to an object about 25 kilometers wide. It's so dense that the mass of all living humans would fit into 1 cubic centimeter of neutron star matter. That's roughly 1 billion tons in a space the size of a sugar cube. Put another way, that's Mount Everest in a cup of coffee. From the outside, a neutron star is unbelievably extreme. Its gravity is the strongest outside black holes, and if it were any denser, it would become one. Light is bent around it, meaning you can see the front and parts of the back. Their surfaces reach 1 million degrees Celsius compared to a measly 6,000 degrees for our Sun. Okay, let's look inside a neutron star. Although these giant atomic nuclei are stars, in and from Europe.
All right, you were able to hear that or see it. I didn't get any complaints, so I think you guys can hear it okay. So neutron stars are just fascinating things, right? Because they're unlike any kind of matter that we have here on Earth. They don't have elements. They're not made of things that we're used to. To have elements, you have to have protons and neutrons and electrons, and to have molecules, you have to have elements, right? And you need to have atoms. So it's nothing like that. It's just neutrons. And of course, the real structure of a neutron star is a lot more complicated than that. But basically, in a oversimplification, a neutron star is just a ball of neutrons that is left behind after a supernova. As I said, it's a massive star supernova, or type 2 supernova to be precise, and so on. So what keeps a neutron star from collapsing under its own gravity? It can't be gas pressure anymore, right? There's no fusion in a neutron star. It can't be electron degeneracy pressure because there are no electrons anymore. It's all neutrons. So what it is very similar to electron degeneracy pressure is neutron degeneracy pressure. So degeneracy pressure of neutrons. And it's again the same idea. Neutrons cannot occupy the same place at the same time with the same momentum. So they start moving faster. This creates a pressure, and that's how a neutron star is supported. Neutron stars have very interesting qualities, and I'm actually going to sort of skip them. I'm going to tell you very, very little about them, but if you're interested, your textbook talks more about them. Neutron stars are, as the video said, they're very small. They're about the size of a city, 10 miles or so, or something like Riverside. And remember that they used to be the core of a really large star. So because something that was several solar masses of mass was compressed into something as small as a city, they end up being incredibly dense. And I like the video because it gives you several examples, but here's another one. 1 teaspoon of neutron star would weigh as much as a mountain, right? I like what they say, the mass of every single human on Earth could fit into a sugar cube. So they're incredibly dense, much more so than white dwarfs. Other things that happen because they were compressed so much, because they shrank so much, is that they rotate very, very fast, right? Remember conservation of angular momentum, the radius, so they were rotating to begin with, but then as they compressed to this very small radius, so the radius became much smaller, but something else had to increase, which is the speed with which they rotate. It is a little crazy to imagine. I mean, some of them rotate several times per second. So imagine something as big as a city rotating several times per second. It is incredibly fast. And another thing that is interesting about them is that their magnetic fields are very, very strong. So stars have, in general, stars have magnetic fields. And if you remember, they come out of the one pole, go into the other. Now imagine that you compress all of that. And so the magnetic field lines get really tight, very close to each other. And that makes neutron stars, that causes neutron stars to have incredibly strong magnetic fields. So now something that I won't be able to get into just because there's not enough time in one quarter, but because of those magnetic field lines, neutron stars can emit a type of light that we haven't covered in this class. It's called synchrotron radiation. Don't worry about writing it down because it's not going to be on the test. But this is what this little video here illustrates. This light, due to the magnetic fields, comes out of the poles of a neutron star. And so a neutron star ends up being kind of like a beam, like a lighthouse that is rotating, and with these beams of light and going out of the poles. Now imagine that it's rotating and it happens to point directly at you and it's rotating, then it would be like a lighthouse. You would sometimes see a flash of light and sometimes you wouldn't. And so answering one of the questions in the chat, can we see a neutron star from Earth? We can see many of them because of this. They basically look like lighthouses or like flashing things, and they're called pulsars. And again, I'm not gonna have any of this on the test. It's just that I'm sure some of you have heard about pulsars. That's what it is. Pulsars, because they seem to be pulsating, but they're not really pulsating. It's just that sometimes they beam, their beams point at us, and that's why they look brighter. They were discovered a really long time ago. They didn't know what they were. They actually thought maybe they were extraterrestrials who were sending us signals. And it took quite a long time actually to figure out that they were actually neutron stars. So the very first name that they gave them was little green men, because they thought they were like ETs or extraterrestrials. All right, so they're very, very interesting, very fascinating. And, there's a whole field of study for neutron stars. People are still trying to figure out many things about them. When we see, I have a question here. When we see a twinkling looking star, is that a neutron star? No, this light, this beam, you actually can't see it with your eyes. Sometimes you can, but I mean, you need telescopes in order to be able to see it. Mostly you see this as radio signals. So radio light is how you see it most of the times. Right. Okay, so just like white dwarfs, neutron stars have a limit to how massive they can be. If the mass of a neutron star exceeds about 3 solar masses, then neutron degeneracy pressure cannot increase anymore. It's the same idea. It's if it gets to about 3 solar masses, neutrons reach the speed of light, and they can't keep going faster and faster because nothing can go faster than the speed of light. And so therefore, neutrons, they can't accelerate anymore. And so they cannot increase the pressure anymore. And so if there is gravity such that it's greater than that, then the star will collapse. So if the inert core, meaning inert, remember, not fusion, if the inert core of a star ends up having more than 3 solar masses, than 3 times the mass of the sun, we just don't know of any other type of pressure, right? I mean, first there was electron degeneracy pressure, but then Chandrasekhar figured out that it can only sustain 1.4 solar masses. And then there's neutron degeneracy pressure after that. And we need a Chandrasekhar because we haven't figured out exactly what the number is, but it is around 3 solar masses. After that, we cannot, I mean, the star cannot oppose gravity anymore, so, or cannot balance it anymore. So then if a core is more than 3 solar masses, when it collapses, right, when it stops having fusion, then what we end up with is a black hole. And this is how black holes are created, or one of the ways in which black holes are created. At the end of the life of a star, once it exhausts all types of fusion, it gets to be iron, it cannot fuse anymore, the core collapses, the entire star explodes like a supernova. And if the core has more than 3 solar masses, if it is more massive than that, then it will end up becoming a black hole. All right, so that's the third type of core. If it has more than 3 solar masses, gravity wins, nothing can prevent a collapse. And so it collapses. It collapses to what size? To infinitely small size. And that's one of the things that is so weird and so hard to wrap your head around in black holes. All right, so for the rest of today, we'll talk about black holes, and then next class too, and the next one too. And again, this is because well, because it's a really fun, actually, there's a reason. Whenever I taught astronomy before I created this class, I realized that people would talk about black holes for about half a class, and then students would have so many questions, and they would, it was kind of not satisfying, right, to only have half a class. So then I decided, okay, let's make it a whole week. So that's why we'll talk about black holes for the rest of the week. All right. So black holes, actually, let me take this opportunity to try to change networks again. So give me a minute or a second, and I'll try to do that. Let's see. Maybe. All right. So hopefully I won't freeze anymore. Let me know if I do. And oh no, my internet connection is unstable. I should have stayed on my hotspot. Well, I'll give it a try. Let me know if it doesn't work. I have a couple of good questions. How and why does the mass of a neutron star or a white dwarf increase? That's a great question, right? I mean, and let me go back to that slide so a white dwarf, first of all, if the core of a star has about 1.4 solar masses, it can survive as a white dwarf. How would it ever increase? And that's a great question. The only, I mean, not the only way, but a great way for it to increase is imagine that it's close to another star. and that it gets close enough to that other star. They're going around each other. And let's say the other one suddenly becomes a red giant, so that it gets a lot closer to the white dwarf. If that happens, some of that material from the companion star can go into the white dwarf, and that can make it increase its mass. That is something that later on we're going to learn that leads to another type of explosion, because after 1.4 solar masses, electron degeneracy pressure cannot work. Neutron stars, or for example, you can have two white dwarfs that are going around each other and then they merge with each other. So again, it can either explode, or maybe it just merges, and then the mass is too high, like let's say it's about 2 solar masses, so then it becomes a neutron star. And same thing with a neutron star. So a neutron star is close to another star, they're going around each other, and then some of the mass from the other star falls into the neutron star, and then the neutron star can become a black hole. Or two neutron stars are going around each other, they merge, they become a black hole. And we're actually going to cover a little bit of this next class. So that's what I mean by they could increase their mass. If more mass got dumped into them, they would increase their mass. Or else, consider just how much mass ends up in the core of a star after all of the outer layers are expelled. How much of the mass ends up in the core? And so then if it's less than 3 solar masses, then it'll be a neutron star. If it is more than 3 solar masses, then it'll be a black hole. I don't understand the question, sorry. All right, so I'll get back to your questions when I show the next video. So let me move on here. So let's just talk about what is a black hole. What is the definition, the basic definition of a black hole? Well, a black hole is a region of space-time. What do I mean by space-time? Well, I mean, we have 3 dimensions of space, right? We have up and down, and left and right, and front and back, right? We're familiar with that, or in math, X, Y, and Z. So we have 3 dimensions. And then we have another dimension, which is time. Usually with time, we're always going forwards, right? We don't go forwards and backwards. In the universe that we know, time is always going forwards, but it is another dimension because we're always moving through it. We're moving from one moment to the next moment. So in physics, we put those two together. We put space and we put time together because we move through space and we move through time. So black hole is a region of space-time in which gravity, the force of gravity, right, is so strong that absolutely nothing, not even light, can escape it. All right, so that's sort of the basic definition. So let's talk a little more about this. Okay, so I have the question, is that what the 4th dimension is? Yes, so 3 dimensions of space, 1 of time. So that's time would be the 4th dimension. That's right. Let's talk about what do we mean by it cannot escape it, right? So we're talking about gravity, and gravity, we're very familiar with it. On Earth, for example, it's the thing that makes us fall down instead of falling up. And you know that on Earth, if you throw something upwards, it'll go up for a little while, and then it'll slow down because of gravity, because gravity is pulling it back down, and then it'll eventually come back down because of gravity. But you can imagine how if you throw it fast enough, eventually it should be able to escape the gravitational pull. So we call, how fast do you have to go in order to get out of the gravitational pull of an object? That's what we call the escape velocity. So escape velocity is defined, it really should be escape speed, but you know, we got stuck with the escape velocity. I mean, velocity, why? Because the direction is in the opposite direction as the object that is trying to escape. So the escape velocity is the speed or the velocity necessary for an object to completely escape the gravity of a large body. So for example, Earth or the sun or a planet, or we'll talk about the black hole. Just like I did with gravity, I showed you the equation. You do not need to memorize it, but this is actually derived from the gravity equation. So in order to calculate this escape velocity, it's equal to the square root of 2g, those are just constant, of the mass of the object divided by the radius, and square root of that. So again, I don't want you to remember that equation, but what I want you to see is that the escape velocity depends on the mass of the object, but it also depends on the radius. And you will need a greater velocity if the mass is greater, right? But you also need a greater velocity if the radius is smaller, because the radius is in the denominator. So let me actually, I have something that is called the Newton's canon. Let me show you. I found this applet on the website. Let's see if you can see it. Right, there you go. So the idea is, if you have a cannon on top of a mountain on Earth, and you fire it with a certain speed, it would go just some distance. Of course, intuitively that if you increase the speed with which you fire, the bullet will go further away. And if you keep going, if you make it much faster, right? I'm increasing the speed here, you fire it again, every time it'll continue to go faster and faster and faster. So let's go even further. You can imagine how at some point it'll go so far that it's not going to hit ground anymore. And it'll go all the way around. And actually, this is called Newton's canon, because Newton figured out this is what's happening with the moon. The moon is actually just going around Earth. It's falling around Earth because of gravity, but it's just not hitting Earth because it's high enough. But anyways, you can imagine how if you have a speed that is fast enough, eventually, instead of getting an object that continues to orbit around Earth, eventually you will be able to escape a planet. And so a planet, or the sun, or a star, or a moon, whatever it is. So each planet has its escape velocity, and the way to measure it, or to calculate it, sorry, would be by using this equation, which I will not make you do. But I just want you to see that if you have two planets or two objects that are the same size, the easier one to escape from will be the one with the smaller mass. In the same way, the easier one to escape from will be the one that has the bigger radius, because radius and mass both contribute to this escape velocity. So, all right. So let me do a poll here. So, given that the escape velocity depends on mass and inversely on radius, what happens to the escape velocity of an object if you shrink it? So let me give you a, well, this is 4 choices, sorry about that. So what happens to the escape velocity of an object if you shrink it? A, it increases, meaning it gets harder to get out of the object. B, it decreases, meaning it gets easier. You can go slowly and you can still escape an object. Or C, it stays the same. There is no D answer. So let me end this because I think it's a pretty easy one and everybody's getting it. Well, most people are getting it. All right, so share the results. So it was actually pretty split, A and B. So what happens to the escape velocity of an object? Meaning, is it easier or is it harder to escape an object when you shrink it, when radius becomes smaller? So a little more people chose A than B. A is the correct answer. It increases. So let me put it this way by pointing at the equation. So if you leave M the same, right, and 2G, again, 2G are constants, you forget about those. So if M stays the same, but this number becomes smaller, this entire number, right, the escape velocity will become bigger. So if the radius becomes smaller while keeping M the same, M is the mass, then the escape velocity will be greater. This is because imagine you're in a planet and, you know, like Earth. So it's hard to get out of Earth. You have to be going on a spaceship. You have to go to SpaceX or NASA, get into a rocket, and then that way you can reach the escape velocity. But what if you're standing on that same Earth and that same Earth is shrunk, right? With the same mass, you keep the same mass, but it shrinks. If the radius of the Earth becomes smaller, then you're going to be experiencing a higher or stronger force of gravity because you're closer to the center of Earth. That's radius. Remember, this gravity depends on distance. And if you're closer to the center of Earth by when it gets shrunk, then you experience more gravity and it's harder to get out. So again, with this poll, what happens to the escape velocity of an object if you shrink it? The right answer is it increases. All right. So basically anything can become a black hole if you compress it enough. And so let me give you some numbers, not for you to remember them, just so that you get an idea of how this escape velocity works. So let's take the Earth with all of its mass, you know, with the mantle and the core of the Earth and the oceans and the people and the cows and the hamburgers and everything that is on Earth. So if the Earth were the size of Earth, which it is, the escape velocity is 25,000 miles per hour. That's how fast you have to be going in order to go out of Earth and not fall back again. Now, if you were to take all of that Earth and shrink it, remember keeping all of its mass, but if you were to shrink it, you make it more dense, and you made it the size of the moon, right, which is significantly smaller than Earth, then the escape velocity, you know, you plug in the numbers for escape velocity, and that escape velocity would almost double. It would become 48,000 miles per hour. If you continue to shrink it, if you make it smaller and smaller and denser, so that the entire Earth is now the size of the UCR campus. So at that point, you would have to be going at 25 million miles per hour in order to get out of that imaginary Earth that is very small, but with a very high mass. So now you can see where we're going, right? The more we shrink the Earth, the faster we have to go in order to get out of Earth. So if we were to keep shrinking it and shrinking it and shrinking it so that we get it to the size of a pea, of a marble, right? If it gets that small, the entire Earth with all its mass, and this is like so difficult to conceive of, right? Putting everything into something that small. Anyways, if you could do that, then the escape velocity of that little pea would be this number, 669,600,000 miles per hour. That's the speed of light. So at that point, what happens? Nothing can go faster than that. So if you shrink it a little more, that becomes a black hole, because at that point, rockets cannot escape. Super incredible rockets that we haven't invented yet cannot escape either. And light, which is the absolute fastest thing that we know, cannot escape either. So if you can shrink the Earth into a size of about 1/2 inch with all of its mass, right? Light would not be able to escape. You would shine a flashlight up and the beam would just go up and then back down, just as if it was a ball that you're, throwing up, and it would come back down. So at that point, the Earth has become a black hole. Of course, it is impossible to do that, right? We cannot make the Earth into a black hole. We don't have the technology to do that. It would be, I can't even imagine how that would happen. But that's what happens with the cores of stars that are more than 3 solar masses when they collapse. Nothing can keep them from getting more and more and more and more compressed. So then they reach that critical size where the even light would not be able to escape, and then a black hole is formed. So again, nothing can travel faster than light. We will talk about this again and again and again for the rest of the quarter. Light is the absolute fastest thing. So if the escape velocity of a body is equal or more than the speed of light, then nothing can escape, right? Not even light. And so we call that object a black hole. All right, so if there's, well, actually, I have a couple of questions about this escape velocity, but let me give you a poll so that you can think about these things. So it is a couple of polls, actually. So I'm showing you 2 planets, a purple and a green one. And for one of the questions, it is, they have the same size, they have the same radius, but they have different masses. And for the second question, they have the same mass, but different radii. So let me give you the poll. All right. So which of these 2 equal sized planets has a higher velocity? Answer A, the one that has a mass of 10,000 kilometers. B, the one that has a mass of 1,000 kilometers. Again, let me rephrase the question. Which of these 2 planets which have equal sizes, equal radii, from which of them is it harder to escape? Which of them has a higher escape velocity? Which one has a higher surface gravity? That's another way to put it. That's question number 1. For question number 2, which of these 2 equal mass planets, right? So here now you have 2 planets that have exactly the same mass, but one of them is a lot smaller in radius than the other one. So from which of these 2 is it harder to escape? Or which of these 2 has a higher escape velocity? The one with the smaller radius or the one with the larger radius? While you guys are answering that, let me get to a couple of the questions. So yeah, I wanted to address why is the escape velocity increasing when the size decreases? By size, remember, size is length or radius, diameter. But I am talking about keeping the same amount of mass. So if you keep the same amount of mass, but you shrink the radius, if the radius becomes smaller, then the gravity that you feel is greater. Because remember, when you're closer, when 2 objects are closer together, or when you are closer to the center of Earth, you experience a greater gravity, right? So therefore, it is more difficult to get out. So, okay, let me end the poll because I think everybody answered already. and share the results. So which of these two equal-sized planets has a higher escape velocity? The one with the greater mass. Very good. The one with 10,000. So 68% of people answer that. The second one, which of these two equal mass planets has a higher escape velocity? And 88% of people answer the right one, which is the one that has the smaller radius. Very good. So again, if it has a higher mass, you experience more gravity. More mass means more gravity. But remember, distance plays into gravity too. Distance is a factor. And the closer you are to either the center of the planet or the center of the star, or the closer you are between two objects, then the greater the gravity. So that's why in the second one, and the majority of you got that right, but in the second one, answer A is the correct one. The tiny little planet with the same amount of mass is the one that will have the higher escape velocity. Oh, if the sun exerts gravity on the planets, how is it that the moons are not being attracted to? They are. The moons, everything in the solar system is being attracted by the sun, but the moons are a lot closer to the planets. The moons are a lot closer to the planets that they orbit, so they feel a stronger gravity from the planets. Again, it's this distance. And I think during this class, I have been emphasizing a lot more mass, more gravity. But now it's time to also emphasize less distance, more gravity, right? Smaller distance, greater gravity. All right, we only have 3 minutes, so I just get to talk about a few more things. So we will be talking a lot more about black holes. Today, in the last 3 minutes, I will talk a little about the main parts of a black hole, like the taxonomy of a black hole or the anatomy of a black hole. Next time, we'll talk about how do you detect them and have we ever seen one? And then after that, we'll get to the violent part, which is what happens if you fall into one. And we'll end up by talking about a little bit what's true, what have we actually observed, and what is just science fiction when we talk about black holes. All right, so if you were to see a black hole that was roaming around, that this is more or less what it would look like. It would look like a spherical thing where the light at the edges would be bent. We'll talk more about that later. But basically you wouldn't see anything coming out of the black hole itself because nothing can escape the black hole, not even light. So what do we know about black holes, about their parts? Well, in the very center of that sphere that I was showing, you have all of the mass concentrated. We call that a singularity. And it is the place at the very center of the black hole where, at least in principle, all matter, everything, all the mass that was making up the core of a star gets crushed into an infinitely small and dense point. What does that mean? Honestly, it's hard to wrap my brain around it, right? Like, what do you mean that something that was so huge, humongous, now it doesn't even have a size? It's infinitely small. It's very difficult to think about it. And I don't think anyone has an easy time with that. Maybe mathematicians, because mathematicians think about infinity and you know, infinitely big, infinitely small. But the rest of us normal humans, I think it's very difficult to understand. And so singularity is a word that comes from math, and it is and so it is singularly small, right? It is incredibly small. So that would be at the center of a black hole. And then I got several questions about this word before, and here it is. So event horizon. Event horizon is basically the boundary, you know, from the singularity, you know, out. Like it is the boundary it's the distance at which the escape velocity is equal to the speed of light. So again, remember, gravity increases with decreasing distance. So if you're closer to the singularity, you experience more gravity. But if you get far away from the singularity, then you experience less gravity, even though it's still a black hole. So the event horizon is that place where if you were to get closer to the singularity than that event horizon, then you would never be able to escape. If you're just outside the event horizon, then you still have a chance of escaping. So you can think of the event horizon as being the surface of the black hole. You can't see anything inside, but you can see right outside of it. And so it's the boundary, right? That's like the limit of where the black hole is. So nothing can escape from within the event horizon because nothing can go faster than the speed of light. All right, so it's we're out of time. Sorry about the technical difficulties. I have a lot of questions, so I'll be happy to stay around and answer them. And I will see you on Wednesday otherwise. So let me stop recording and I will see you guys later, and I will be answering a bunch of questions.